Okay, so today we're going to look at how things dissolve. So what's going on when things dissolve? When you add sugar to your tea in the morning, or when you add salt to your water when you're making pasta, what is happening? It is a process where the solute molecules move into the spaces of the solvent molecules. Right? So the solvent molecules, if you have a glass of water, it's made up of water molecules, but the water molecules have spaces between them. They're not stuck together. They're not even very close together. They can move past one another. So what happens is that when you add salt to water, teeny tiny particles of the salt break off of the big chunk and they move in between the water molecules. So we have that's called dissolving. We also have crystallization. Crystallization is the opposite of dissolving. And so when you have a bunch of ions floating around in the water, sometimes they collide and sometimes they stick together, in which case uh, it will increase the mass of crystals, right? This would be the solid part increases. Um, so dissolving and crystallization is what's called a dynamic equation, meaning I can make it go both ways. Okay, if I have a glass of water and I start shaking salt into it, eventually there will come a point where no more salt will dissolve, and then you'll see solid salt start to build up on the bottom of the glass, right? I could add more water to that, and that salt that's on the bottom of the glass that's solid would go into the solution because now there's more water molecules for them to go between, right? So things that are dynamic, the process can go one way or it could go the other way, and that's why you have the two arrows there. So you could go from solute and solvent to a solution, right? And that's called dissolving. Or the solution could go back to being some solute and some solvent. That's crystallization, right? So the solution, this is homogeneous. And the solute plus the solvent before it dissolves, this is heterogeneous. You can see two things. Heterogeneous. Okay. And then there's a point of equilibrium. So if you start shaking salt into a container, there will be a point where nothing else can dissolve, right? So the rate of dissolving and the rate of crystallization will be equal. Now, the steps of forming a solution. So there are 3 steps to forming a solution, okay? Number 1, the solute particles will separate, right? So if you have salt, for example, the salt particles will separate from one another. Okay, so that means there are forces holding them together, and something will overcome that. Okay, um, which usually means we have to expend energy, right? We have to expend energy to overcome the forces holding them together. We must expend energy to overcome the forces holding the solute together. Okay, then the solvent particles separate. They move away from each other. And this is also endothermic because there are also forces holding the solvent together. So the first two products are endothermic. Endo means into, and thermic means heat energy. And it kind of makes sense because if you've ever tried to dissolve, let's say, a bag of tea into cold water, it doesn't usually work very well. It's usually a very slow process. You have to keep it in maybe overnight. But if you try to dissolve tea, a bag of tea into hot water, it gets all of the heat energy that it needs, right? And then it's very easy to make tea. The third step is where the solute particles are attracted to the solvent particles, right? And this is usually an exothermic process. This means it releases energy. Okay, so you can see here we have step one. We have the solute, and it's going from all together. Actually, I want to write a few things here. Right, you can see that there are forces holding the particles together. This is, we add energy. And the particles separate. Here we have the solvent. We also have forces holding those particles together. We also add energy, and those separate. And step three is, for some reason, not visible there. I don't know why. Step three, the particles will go in between each other. Right, so they'll mix in between each other. It says for dissolving to occur, the release of energy, step three, must be greater than the energy that is absorbed, steps one and two, right? So step three has to release more than step one and two absorb. Oops. Dissolving of a solute in a solvent will occur if the forces holding the individual particles within each are weaker than the forces that could form between the solute particles and the solvent particles. The greater the attraction between the solute and the solvent particles, this is important, the greater attraction between the solute and the solvent particles, the more soluble a solute is in the solvent. Because if they're attracted to one another, they'll go closer to one another, and then more of the solute can mix in. Now we need to talk about water, the universal solvent. Okay, that's very important. Water has the ability to dissolve a number of molecules, right? So it can dissolve a lot of things. And And it's also special because water has higher than expected melting and boiling points. It has a high surface tension. And this is because water is a polar molecule. So, way back in the first unit, we were talking about whether molecules are polar or nonpolar. And water is a polar molecule. So, oxygen has an electronegativity of 3.4, and hydrogen has an electronegativity, should write En, an electronegativity of 2.2, right? So when we do the electronegativity difference, 3.4 minus 2.2 is 1.2, and this is between 0.5 and 1.7, right? So this is a polar covalent bond. Right? So that's one of the conditions for having a polar molecule. The other condition, right? So that, okay, so let's draw our little charges. So all the all the hydrogens are partially positive and all the oxygens are partially negative, right? So if we were to draw the dipole arrows, you can see that they're both pointing in the same direction, right? And the dipoles don't cancel. So water is polar. As a molecule, not just as a bond, as a molecule. Okay, so it says the oxygen end of the molecule has a partial negative charge, while the hydrogen end of the molecule has a partially positive charge. So what attracts the negative end? Something positive. And what attracts the positive end? Something negative, right? So if whatever water is mixing with has some sort of charge, it will tend to be very soluble. Water also has the unique hydrogen bonding, which means it's sort of superpolar. It's very, very extrapolar. But it also lets it have uh, properties like being a liquid at room temperature instead of a gas, like most things its size, right? It's just really sticky to itself. It allows it to have high surface tension. So these are the hydrogen bonds that I'm coloring in, right? Water has very strong forces holding molecules together. I'm going to write that down. Water has very strong forces holding it together. Actually, I'm going to amend that. Very strong forces between molecules holding them together. Because they hold water molecules together, these are intermolecular forces. Okay, the negative end of the oxygen and the positive end of the hydrogen, they attract each other. So this is minus, this kind of minus, not fully minus, and this is kind of plus, right? And the same thing will happen down here. The hydrogen is kind of positive, the oxygen is kind of negative. They will form these hydrogen bonds. These partial charges also attract ions. So here we have, this is sodium chloride, and that's table salt. We know that dissolves in water. Table salt is made up of a sodium cation, uh, a positive ion, and a chlorine anion, a negative ion, right? So the negative chlorine is attracted to the positive hydrogen, and the positive sodium is attracted to the negative oxygen. Okay, these are also sort of intermolecular bonds. They are called actually, could have sworn, maybe not yet. Maybe it's on the next page. Okay, the force though between water and sodium chloride causes the ions to move away from one another. So it breaks the ionic bond between the sodium ion and the chlorine ion. It overcomes those electrostatic attractions. And then what happens is an ion gets surrounded completely by water molecules, in which case this is called hydrated. So you can see here, we have a hydrated chlorine molecule. And you can see that the chlorine molecule is lined up with all of the positive hydrogen ends of the water molecules that have surrounded it, right? Because chlorine is negative, it attracts the positive ends of the water. Okay, so this is called hydration. You'll also notice the other ion also gets hydrated. So because lithium is positive, it attracts the negative. The negative oxygen end of water. Okay, so you can see here lithium is positive, and you can see it's attracted to the negative end. The oxygen end of each water molecule lines up so that the oxygen is closest to the lithium. So this hydration step only happens if water is the solvent. You might hear if something like ethanol or air is a solvent, you might hear the word solvated, meaning it's surrounded by solvent. Sodium chloride, lithium chloride are both electrolytes. Electrolytes are solutes that dissolve in water to produce ions, and they have the ability to pass electric current through the solution. So if you have a solution of salt water and you have some wires and a light bulb, and a battery, you need a battery too, you can make the light bulb light up. Because it's an experiment that involves electricity and water, I suggest that you go look it up on YouTube, or maybe I will post a video link of how you can use salt water, which is an electrolyte solution, to make electricity flow. You can also use things that are salty but also juicy to complete circuits to run electricity through. For example, you can run electricity through a potato or a pickle, because both of those things have dissolved ions in them, but they also have water in them. Of course, I obviously don't recommend running electricity through anything as an experiment because you can electrocute yourself. But again, I will try to post a video. Non-electrolytes are solutes that may dissolve in water, but they do not produce ions. So sugar will dissolve in water, but it's not an ionic compound, and it does not break down into ions. And if you try the same thing with salt water, with sugar water, so you would put some wires and attach them to a battery and attach the battery to a light bulb, right? And you would stick two ends of the wire in the sugar water, nothing happens. The light bulb doesn't light up. Electrolytes are, of course, important for our bodies, right? Electrolytes are in some sports drinks like Gatorade, and we need electrolytes in our body to help our muscles and our nerves behave properly. But when you sweat, you lose ions. So people who play sports a lot drink sports drinks to replace the ions in their body. If they don't, they could get cramps, muscle cramps, or they could get nerve twitches. And if you do get a muscle cramp or a nerve twitch, one thing you can try to do is drink pickle juice because it's salty and it will return some of the necessary ions to your body. Anyway, ionic compounds like salt and covalent compounds like sugar, they dissolve differently. So we're going to take a look at ionic compounds and how they dissolve, and covalent compounds and how they dissolve. Ionic compounds do something called dissociation. So ions, when an ionic compound dissolves, the ions separate from the ionic crystals and they become individual ions. Okay, so for example, here we have sodium chloride, a big chunk of salt. Okay, and you can see there are some smaller blue circles. Those represent sodium ions, right? So I'll put the little plus on them because they're positively charged. And the chlorine is a big white circle, and they're negatively charged, right? So you can see you have a bunch of positive and negative things, and they're held together by those electrostatic attractions by ionic bonds. Then we put it in some water, and what's going to happen is that because the water, right? So remember, water kind of looks like this. Because the water has slightly positive charges and slightly negative charges, right? The ions are going to start to move towards the water molecules. They're going to be attracted to the water molecules. So they're going to break up from one another and go chase some water molecules, right? We can write a dissociation equation describing what happens here. Even though it's a physical process, we can write an equation for the change. So sodium chloride, which is a solid, will become aqueous sodium positive ions and aqueous chlorine negative ions, right? So this shows the breakup of the ionic compound into its particles. So that's step one. Okay, remember the solute particles move apart. Okay, step two, we have the solvent particles moving apart. So maybe over here, right, you have that chlorine ion, right? And so this water molecule might move away from its neighbor because it's attracted to the chlorine, right? So these will separate and go farther apart from each other. It will break the hydrogen bonding, right? Those are the forces. This is breaking the hydrogen bonding. Okay, so now those two water molecules can move away from each other. So here we are, this step we are breaking the ionic bonds, right? And here we're breaking the hydrogen bonds. Okay, hydrogen bonds are called intermolecular forces, forces between molecules. We are not breaking the bonds holding the oxygen to the hydrogen. We're not breaking those. We're breaking the bonds that go between molecules. Okay, the water will stay as one oxygen attached to two hydrogens. Intramolecular forces, like ionic and covalent bonds, are stronger than intermolecular forces. So if you add some energy to something, the intermolecular bonds are going to break before the intramolecular bonds do. The intermolecular forces determine, besides solubility, they determine melting point, boiling point, and some other properties. Okay, so here's the intermolecular force. This is what is getting broken. Step 3 is hydration. So in hydration, you can see now the sodium is fully separated from the chlorine, right? They've gone their separate ways and they have been surrounded by a sphere of water molecules, right? So they're completely cut off from each other. The sodium ions attract the water, and the negative side of the molecules surround the positive sodium ion. The chlorine ions attract the water, and the positive side of the molecules surround the negative chlorine ion, right? So opposites attract. So this is between a dipole, right? A dipole and an ion. So these are dipole ion forces. What is the purpose of hydration? Why does it happen? Because it stabilizes the ions, because they no longer have each other to stabilize, right? The water molecules stabilize the ions instead, and it prevents the ions from attracting one another, okay? The intermolecular force between a polar molecule like water and an ion is referred to an ion-dipole interaction. There is competition between the intramolecular forces holding the solute particles together and the intermolecular forces between the water and the salt. Okay, if the forces holding the solute particles are together are stronger, it doesn't dissolve. If the forces attracting the solute particles away from each other is stronger, it will dissolve. And as a reminder, you don't have to think about this too much because you can predict which ionic compounds will dissolve using your solubility table from Unit 2, or Chemical Reactions Unit. And then only ionic compounds undergo dissociation. So we'll look at covalent compounds next, but you can show this dissociation equation. So to figure out what it's going to be like as ions, right? You're going to have to sort of uncross the subscripts. So this 2 came from CO3 2 minus. And the CO3 is not in brackets, so that means it gets a 1 subscript, right? you can look up the charges for elements on the periodic table. And you can look up the charges for polyatomic ions on your reference sheet. So the charges part is easy. But you'll notice there are 2 sodium ions, and that's because sodium has the subscript 2. So whatever the subscript is, it becomes a coefficient when they break up into ions. Okay, there will be some practice, so you can practice coming up with this tonight. How do covalent or molecular compounds dissolve? This would be like sugar. Sugar is we could do glucose, or we could do sucrose. Sucrose is C12, H22O11, I think. Molecular, so there's no metals here. So how will this dissolve? So it says molecular compounds vary in how easily they dissolve in water. Not all molecular compounds dissolve in water. Some covalent compounds contain polar bonds. So for example, alcohol, sugars, and they're soluble. So things that contain polar bonds are soluble in water. These compounds will dissolve, but they will not undergo dissociation, or they will not make ions. Okay, so no ions are formed. How can we tell if we're looking at a molecular compound whether it will dissolve? Well, there is a rule called like dissolves like. So substances that have similar intermolecular forces will dissolve in each other. So polar substances will dissolve other polar substances, right? So ethanol, this is ethanol. Okay, in ethanol, the red thing is an oxygen molecule, and the white thing is a hydrogen molecule. So this thing has hydrogen bonding, right? So water has hydrogen bonding, and ethanol also has hydrogen bonding, right? Which means the partially positive hydrogen molecule will be attracted to the partially negative oxygen molecule, and this creates a hydrogen bond. Nonpolar substances will dissolve in other nonpolar substances. So for example, oxygen does not dissolve very well in water, but it dissolves much better in nitrogen. Right? If you compare how much oxygen dissolves in nitrogen and how much oxygen dissolves in water, nitrogen will be quite a bit more. So if the molecular compound has no positive or negative charges, then it will not attract water molecules, and it is insoluble. It does not dissolve in water. Oil and grease are insoluble in water. These compounds are nonpolar, and they have only van der Waals forces. As a result, water will continue to hydrogen bond to itself and exclude the nonpolar molecule. Nonpolar molecules are usually soluble in other nonpolar substances like benzene and kerosene. So you might know solvents if you've ever tried to paint a room, right? Paint is a nonpolar substance, or maybe you've tried to paint your car. Paint and I'll put nail polish. Are nonpolar and they don't come off with water. It would be very inconvenient if every time you washed your wall, your paint came off, right? They're nonpolar by design, so they don't wash off easily. Okay, and they need special solvents. So if you spill paint, you'll have to get something called mineral spirits to clean it up, or maybe sometimes paint thinner, which is acetone. And nail polish is also usually acetone as well, right? So acetone is not very polar. Nail polish and paint aren't really polar, so they dissolve in each other. So let's take a look at this. Vinegar dissolves in water. So vinegar is a polar substance. Oil does not dissolve in water. Oil is a nonpolar substance. Vitamins A, D, E, and K are not eliminated in urine. Urine is mostly water. And can accumulate in fat cells. Fat is nonpolar. So these vitamins are nonpolar substances, right? So all of the vitamins that you have to take with food, those are nonpolar substances. And the reason why you have to take them with food is because they don't dissolve in water. But vitamin C is soluble in water and therefore is a polar substance. And the best thing about polar vitamins is you can't overdose on them. You can't take too much vitamin C because your body will just pee it out. But A, D, E, and K, you can absolutely take too much in. And some people have even poisoned themselves with fat soluble vitamins. They accumulated in their fat and they became toxic and made the person sick. Some other applications of solubility: washing stuff, getting stuff clean. Okay, some compounds have a nonpolar component to their molecule as well as a polar component, like soap. So here's the thing. You are eating maybe a hot dog or a hamburger and you have some mustard on it and you spill the mustard all over your shirt. Mustard gets its flavor from oils, right? And if you just rinse your shirt underneath some water, the mustard stays there, right? The oils stay there and they can stain your shirt. So what you need is something to connect the nonpolar mustard oil with the polar water. And what that thing is soap. I don't know why it didn't put the whole molecule. Soap has a big part that is nonpolar. It is made of C and H bonds, and C and H bonds are nonpolar bonds. But at the very end of soap, it has a polar part, right? So this part, this nonpolar part, will attach to oil, and the polar part will attach to water. So then, when the water washes the one end of the soap away, the tail, which is attached to the oil, also gets washed away. And that's how you clean your clothing. Um, with chemistry. Another application of this are proteins and enzymes. So some proteins we make in our body are water soluble and some are not. Proteins are very, very large molecules, and they exist inside of our cells and outside of our cells. And they navigate through a very aqueous, watery environment. Most of the protein may be nonpolar, but because they have to navigate through water, they have their polar groups on the outside where they're exposed to water. So the inner part of this big protein, I hope I can make this right correctly. I'm trying to consider what color to use. The inside is nonpolar. The outside is polar, and this allows it to go through the water. Okay, so it says in the graphic on the right, the protein insulin is shown in two views. The interior of the protein is shown in the gray is nonpolar. So these clump together because like dissolve like. The nonpolar bits of the protein like the other nonpolar bits of the protein, and they're all going to try to clump together. The outside of the protein are largely polar groups, which are shown in red, which are able to interact with the polar water molecules. So we can make the entire protein soluble as long as the outside contains some polar bits. So in summary, polar substances will dissolve in other polar substances. And polar substances will dissolve other polar substances and ionic compounds. So if it's polar, both polar covalent and ionic compounds will dissolve in it. Nonpolar substances dissolve other nonpolar substances. That's the like dissolves like. Polar substances will not dissolve in nonpolar substances such as fats, oils, hydrocarbons, or hydrocarbons are like we'll call it like gas and other fossil fuels. Ionization. Okay, so ionic compounds dissociate, right? So NaCl, this is an ionic compound, will break down into a sodium ion that is dissolved in water and a chlorine ion that is dissolved in water. This is an acid. So acids are covalent, but they make ions in water. And that's what gives acids their property. Okay, but we don't call it dissociation when an acid makes ions. We call it ionization. Okay, so in this reaction, a chemical reaction has occurred because HCl did not have ions originally. So we're actually making a chemical change here. It contained a covalent bonding, but with the addition of water, ions can be formed. Right? So this is something called ionization. So both ionic compounds and acids, they will make ions in water. Also, we have factors that affect the rate of dissolving. So everybody's probably tried to make tea at one point in their life. Factors that affect the rate of your tea bag dissolving. Temperature works much, much better in higher temperatures than lower temperatures. So in general, the higher the temperature, the higher rate of dissolving, since the particles have more kinetic energy, and those will overcome the forces holding the solute and the solvent together, right? They collide more frequently, so the rate of dissolving increases with increased temperature and decreases with decreased temperature. Agitation is stirring, is a fancy name for stirring. So you know that if you put a spoon in the tea while you're trying to make it and you swish it around, you circle the spoon in the tea, you will cause the molecules to move more, and then you'll have a higher rate of dissolving since more particles make contact with one another. And surface area, particle size. So if you have ever tried to dissolve a big clump of sugar, right? So if you have sugar and it's all in a big clump because maybe it's been sitting out and the air is humid, this takes a long time to break off all of the particles and dissolve, right? It takes a long time to go here. But if you have big particles, or sorry, smaller particles, right? This takes a short time to where everything is dissolved. If you have a sugar clump, you can compare it against about the same amount of sugar that has not clumped up, and you will see the sugar that has not clumped up, it takes a shorter time to dissolve. We have some homework questions. I'm going to make a separate video about them so you can take a break before you do your homework. These are mostly like comprehension questions, so you can go back to the note and try to answer them.